So, for the last lecture, what I want to do is just give you an introduction into organic reactions. Yesterday we talked about organic molecules, the sorts of different types of organic molecules you got. So we talked about classes and alcohols and alkenes and aldehydes and all that, and functional groups. And what we sort of came to the end, we said that functional groups are the things which enable organic molecules to react. You have this framework of carbons and hydrogens which in and of themselves are not very reactive because carbon-carbon bonds are very strong, carbon-hydrogen bonds are very strong, they're non-polar bonds, and so they don't tend to be where your reactions happen when you do an organic reaction. The reactions tend to be where you have oxygens or nitrogens in your molecule, and so those parts tend to be called functional groups, where the function of the organic molecule is. And so what I want to do today is just have a brief look at some of these organic reactions that you're going to meet in much more detail later in the semester. And I think there's 5 of them. There is 5 of them. One of them you're going to do in the lab today, the last one in fact. But these 5 reactions are called substitution reactions, addition reactions, elimination reactions, oxidations, and then condensation reactions at the end. Okay, so those are the 5 we're going to look at in turn. Substitution reactions are reactions that you get with alcohols and alkyl halides. Right? So you don't get substitution reactions with ketones, and you don't get it with carboxylic acids. You get them with alcohols, and you get them with alkyl halides. And we can summarize a substitution reaction by this general sort of scheme here. So in our general scheme, we have this organic compound here. We've got a carbon, 3 R groups on it. We talked yesterday about what the R groups are. Remember, that's just carbons and hydrogens that we don't worry about. And then we have some group which we're going to call L for the moment. And then we react that with some other thing which we're going to call Nu. And we're going to define what that is on the next slide. And in the course of the reaction, we replace the L with the Nu. Or if you like, we substitute the L for the Nu, whatever those are. Right? So they just swap over. We call L the leaving group. Not unreasonably, because when the reaction happens, whatever L is, it's the thing that comes off. It's the thing that leaves the carbon. So it's called the leaving group. And the Nu thing, the thing which becomes attached to the carbon, has a fancy name. It's called a nucleophile. This may be a word that we haven't come across before. Has anyone seen this word before? 1 or 2? Yep. So this is called a nucleophile. So that's why it's given the symbol Nu. If it's an alcohol, that's the thing that's undergoing the reaction, then the leaving group is going to be OH minus. Right? The thing that comes off is OH minus. Now actually, I wonder if I actually say this. Yeah. What you're going to find, you spend about 2.5 lectures just on these sorts of reactions in Chem 191, and you'll find in the textbook there's quite a big section on this. This is actually not 100% true, but it'll do for today. The subtlety about why this isn't true is something that you spend a lot of time talking about in the lectures, and is a very favourite exam question, right? But for the moment, let's just go with the OH minus being the leaving group. So it comes off as OH minus, right? Not OH or OH plus, but OH minus. If it's an alkyl halide that's reacting, then the leaving group will be the halide ion. So for example, if you start off with an alkyl bromide, then the leaving group is Br minus. If it was an alkyl chloride, it would be Cl minus, and so on. Okay? So that's the leaving group. So the leaving group is the, if you like, it's the thing that makes it the functional group, whatever it is. If it's an alcohol, then the leaving group is the OH, as OH minus. If it's an alkyl halide, then it's the halide ion that leaves as a negatively charged anion. Yeah? The nucleophile can be a whole bunch of things. a nucleophile itself could be OH minus. And so you could write a reaction like this, where you start with an alkyl bromide, where the Br is the leaving group, and if we react that with hydroxide ions, then we can get a substitution reaction where the Br comes off as Br minus and is replaced by the OH minus, and so you turn an alkyl halide into an alcohol. Yeah? And you could equally imagine that if you started with an alcohol, where the leaving group is OH, and reacted that with a solution of Br minus, then you could turn an alcohol into an alkyl halide. And the OH would come off as OH minus, and the Br minus would be the nucleophile and go on, and so you could do that reaction, right? Yeah. Yes. Yes. As far as we need to worry about today, yes, it could well be an equilibrium. Yeah. In reality, they're not always, but it depends on exactly what the nucleophile is and what the leaving group is. Kind of, yeah. And so in general we would call these nucleophilic substitution reactions, because in general the leaving group can also be a nucleophile as well. So you can think about it as just exchanging one potential nucleophile for another on the carbon. So these are nucleophilic substitution reactions, and like I say, we make a big deal about this in the first semester organic chemistry. It's like when you start in the organic chemistry, you start off doing isomers, like we talked about yesterday, and you do that for a lecture or two, and then you get straight into this stuff. So a lot of detail in these reactions. And there it is, you see. In Chem 191, you will study these reactions in great detail to understand how they work on a molecular level and how different factors influence the way that they work. So in other words, how you can, if it is an equilibrium, how you can make the equilibrium be towards the products rather than towards the reactants and stuff. So it's not just a matter of you memorizing that reaction as an example of a substitution reaction, but we're actually going to go and pick that apart and look at the bond breaking process and the bond making process and in great detail how this works. Right? One of the things which will affect how it works is the actual type of alcohol or alkyl halide that you're using. So in other words, what we care about is what the R groups actually are. It turns out that we can classify alcohols or alkyl halides based on the number of carbons that are attached to the carbon which has the OH group on it. Right? So remember, if you look back in your notes, you've got a carbon with an OH and 3 R groups, and we said yesterday that those R groups can be either carbons and hydrogens or sometimes just hydrogen. What we're saying now is that we can classify alcohols into different types based on the nature of those R groups, whether they actually are carbons or whether they're just hydrogens. And so you can imagine a situation where you have an alcohol like this, where here's your carbon, which has the OH group on it, right? So if you like, this is going to be the leaving group in a substitution reaction. And this carbon, in turn, has 2 hydrogens attached to it, and then 1 other carbon. So if you like, this is 1 R group out here. And I've drawn that in as a CH3 group, as a methyl group, but that could be an ethyl or a propyl or anything you like out here. The point is that this carbon has 2 hydrogens and 1 carbon attached to it. If your alcohol is like that, then it's given the name of a primary alcohol. Or if you like this wee symbols, the one with the wee circle, that means primary. So primary alcohol is one where the carbon that has the OH leaving group on it also has 2 hydrogens and 1 carbon attached to it. If the carbon that has the OH leaving group on it also has only 1 hydrogen and 2 other carbons attached to it, then that's going to be called a secondary alcohol. So the carbon, strictly the definition is actually based on the number of hydrogens, but that doesn't make any sense to me. Just go with the number of carbons. If it's got 2 carbons attached to that carbon with the OH on it, then it's secondary. And obviously, if you have 3 carbons attached to the carbon with the OH leaving group on it, then that's called a tertiary alcohol. Okay? And remember, while I've drawn those as being methyl groups, they can be anything. The key is that you've got to have a carbon attached to the carbon that has the OH on it. Right? And so we can talk about primary and secondary and tertiary alcohols in the same way we could talk about primary, secondary and tertiary alkyl halides, where instead of an OH there you might have a bromine or a chlorine. You also come across talking about primary and secondary and tertiary amines, not in the context of substitution reactions, but in other places, right? But again, it's the same idea. It's all about saying how many carbons there are attached to the carbon with the leaving group on it. And so what we're going to find, not today, but later on in the year, is that the actual way that the nucleophilic substitution reaction proceeds depends on whether you're starting with a primary or a secondary or a tertiary alcohol or alkyl halide. Right? If you're just memorizing reactions, then it would make no difference because the reactants and the products are the same. But how you get from the reactants to the products in terms of the way that the bonds break and the new bonds are made is different depending on whether you start with a primary or a secondary or a tertiary alcohol. And it's that sort of thing that we're going to get into, that sort of detail that we get into later in the semester. The second type of reaction that you're going to come across is something called an addition reaction. And an addition reaction is something which is characteristic of alkenes and kind of alkynes, but we don't really do anything about alkynes in 191 at all because alkynes are not really biological molecules. With very few exceptions, you're not going to come across a carbon-carbon triple bond in a biological context. But you see alkenes all the time, right? So addition reactions are ones that as you're going to see, are reactions of alkenes. So you don't get addition reactions with alcohols. You don't get addition reactions with aldehydes. You get addition reactions with alkenes. Yeah? So this whole business about the functional group giving the molecule certain reactivities but not others. And so we can sort of, in general, write that an addition reaction looks like this, where we have an alkene, which has a carbon-carbon double bond in it, and we react this with some molecule which we can sort of generally say is called AB. So the molecule has 2 parts, right? And in the course of the reaction, the AB molecule comes apart, and the A part of it goes onto one of the carbons that is initially in your double bond, and the B part goes on the other carbon that was initially in your double bond. Right? So what we're doing is in the reaction, we're breaking one of these carbon-carbon bonds. Remember I said yesterday that one of those bonds is much weaker than the other one, so it's that weak one that breaks, and then this carbon makes a new bond to thing A, the AB bond breaks as well, and then this carbon makes a bond to A, and this carbon makes a bond to B in the course of the reaction. So we're breaking 2 bonds and making 2 bonds in this reaction. Yes?
If it's just one bond that you're breaking, are they always going to be on the same bond? Like on 2 different ones? Can they not be on the same ones?
No. Can you put A and B both on here?
Yeah.
Then how many bonds would that carbon have in the product? Too many. And the other one would only have 3, yeah? So it's 1 goes on each side. Yeah? Cool. So the reaction involves adding a molecule to the alkene, hence the name addition, right? We take a thing and we stick them together. So it's different to a substitution reaction where we take a thing and this goes on and this goes off. Here we're just sticking 2 things together, right? One of the bonds in the carbon-carbon double bond is broken, and each of the carbons then forms a bond to one end of the adding molecule. In this way, each of the carbons still has 4 bonds. Okay, so here's an addition reaction. Here's propene, and if we react propene with bromine, Br2, this is our AB molecule, so we can write Br2 like this, it's just Br bonded to a Br. So if you like, this is A and this is B, and so one of these bromines goes on this carbon, and the other bromine goes on the other carbon. One of the carbon-carbon bonds breaks, and we end up with a molecule that looks like that, right? Which would be dibromo, what would it be, 1,2-dibromopropane. Another common addition reaction involves the reaction of water with an alkene in the presence of a small amount of concentrated acid. This is one of these things that they certainly make you memorize with sulfuric acid, I think it is. So you start with your alkene and you react it with water and H+, and what in effect you do is you add a water molecule. Actually, I think this is highlighted. No? So if you like, you can think about the H2O as being an H attached to an OH. The H goes on one of the carbons, the OH goes on the other carbon in this reaction. And there's a whole bunch of stuff, more detail surrounding this reaction as well. The old Markovnikov nonsense, which we will get into. We don't actually do. Has anyone heard about Markovnikov? Yeah, we don't really. Markovnikov is an empirical thing where you kind of learn a trick and then it tells you the answer. We're going to do that again, but rather than learning the trick, we're going to show you why the reaction goes that particular way rather than the other way. Right? So again, more detail rather than just memorizing stuff. The acid in this reaction is just there as a catalyst. So it makes the reaction go faster. And so this reaction overall will convert an alkene into an alcohol. And it says, again, you will see much more of this reaction later on. So kind of the opposite of an addition reaction is something called an elimination reaction. So an elimination is where you start with something like an alcohol, and then you lose a couple of bits of the molecule, which go to form a new molecule, and what you're left with is an alkene. Right? So it's basically just the reverse of the thing that we just saw. So here's a primary alcohol, to use our little word that we learnt just before. And in our elimination reaction, the OH on the carbon on the end there and an H on the carbon next door are the two things that come off to give you your alkene and water. Okay, obviously where I had that green blob the first time is wrong, and they can't be off the same carbon. They have to be off, one group has to be off one carbon, and then the other has to be off the adjacent carbon, the one next door. Yeah? Then there's just a wee note there, just to make sure we're all keeping up. The C with the three H's, as it's drawn there, is the same as a CH3 group that's there. Yeah, you probably caught up with that, but just in case people haven't, that's just implying those are the same thing. This reaction produces water, or if you like, the molecule that you start with loses water in the course of the reaction, and so it's called a dehydration reaction sometimes, right? And as we saw before with the nucleophilic substitutions, the way in which elimination reactions go depend on whether you're starting with a primary or a secondary or a tertiary alcohol or alkyl halide. Right? And in fact, what you're going to find is that when you have a nucleophilic substitution reaction happening, generally you will have an elimination reaction happening at the same time. Right? And so then there's some stuff about how you make it do one type of reaction over the other type of reaction when they're both, if you like, competing with each other in the same solution. Right? So there's lots more stuff going on with these that we're going to learn about later. Okay? So that's eliminations. Then we have oxidation reactions, and this is just stuff that you already know about because we did redox last week. You can do reductions as well, but reductions tend to be a bit more complicated, so for the moment we just focus on oxidations. And what you need to know is that you can oxidize an alcohol and you can oxidize an aldehyde. In theory, you can oxidize an alkene, and they do kind of sometimes rashly start talking about that sometimes at school. We're not going to do oxidation of alkenes at all. We're going to focus on alcohols and aldehydes. Note aldehydes, but not ketones, even though they're quite similar in terms of their structure of the functional group. Ketones don't get oxidized, aldehydes do. And so the way it goes is this, that an aldehyde gets oxidized to a carboxylic acid, and an alcohol also gets oxidized to a carboxylic acid. If you're smart and you're very careful, you can oxidize an alcohol to an aldehyde, but then if you're not careful, then the aldehyde will then get oxidized to a carboxylic acid, right? So for the alcohol, it's kind of a two-step process, but in reality, you have to be quite careful if you want to stop it at the aldehyde. To do these oxidations, you need an oxidant, and the oxidants that you can use can be the ones that you've already seen, things like permanganate, right? And permanganate, in fact, is quite often used for doing these sorts of organic reactions. Now, the next couple of slides, I think, are going through doing some half equations and stuff. We might, in the interest of time, not dwell on them too much, but these are certainly things which we would expect you to be able to do later on. Yeah, not obviously for bridging now because I don't care anymore, you don't care anymore, but in a month or two's time, these are things which we're going to come back to, and we would expect you to be able to do these sorts of balancing. And it's all the same stuff that you've seen. So, for example, if you wanted to do that one, right? So here's an aldehyde, propanal. Here's our aldehyde functional group here, C double bond OH. When we do the oxidation, we turn this into a C double bond OH, right? So here in the oxidation, we are actually adding oxygen. Then we could say, write out some balanced half equations and an overall balanced redox equation for this redox reaction, right? The permanganate one, you've kind of seen already, the MnO4 minus with the H plus going to Mn2 plus and 4 waters. Then you would have to sit down and work out balanced half equations for C3H6O, the propanal, going to C3H6O2, the propanoic acid. And you would do this exactly the same way that we saw last week. Balance oxygens by adding water, balance hydrogens by adding H plus, and all that sort of jazz. Okay, so here come the half equations. Like I said, I'm just going to flick through this. If you want, you can do these quietly sometime over a beer. But I'm not going to obviously be testing you on this now, so I'm going to flick through. So here's the permanganate one. We've already seen this last week. This is going to be a reduction. We would start with our C3H6O going to C3H6O2. We balance for oxygens by adding water. We then balance for hydrogens by adding H pluses. Once that is all done, we use total charges to work out the electrons. Turns out that there's 2 electrons on the right-hand side, as there needs to be because it's an oxidation. Yeah, it's losing electrons. Then to combine them, we're going to multiply the top one by 2, the bottom one by 5. We add them all together to get all of that. And then we look and we see that we've got H pluses on both sides. So we can cancel 10 H pluses off both sides to simplify that. We've also got waters on both sides, so we can cancel 5 waters off both sides to simplify that. And we end up with the overall equation like that, right? So it's a little bit curlier at the end because there's some cancelling out, not just of electrons, but of waters and H pluses. But fundamentally, it's exactly the same thing that we've already done, right? So this is not for today, but is for later on. And you could do exactly the same thing for propanol going to propanoic acid if you wanted, right? Or indeed for any alcohol going to any carboxylic acid, well, to the related carboxylic acid. Yeah? And then it just says, note that the process of oxidation adds oxygen atoms to the molecule. This is presumably where the word oxidation first came from. And the reverse process, reduction, involves removing oxygen from the molecule. Like I say, we're not really going to do reduction very much. We used to, and it uses lots of interesting things like these metal hydrides that we kind of talked about the other day. You use metal hydrides for doing this as a way of pulling oxygen out of a molecule. But it's not really very biological to do that, and hence in Chem 191, that's kind of been shunted out, and you learn about that somewhere else. Okay. So that's oxidations. And then the last thing is condensation reactions. And these are a little bit more involved. And you're going to do one of these in the lab this afternoon, so that you're going to have a chance to sort of go back over how these sort of things work. But they're reactions that between a carboxylic acid, and I note I've put carboxylic acid in quotes there because it can be a carboxylic acid or something like a carboxylic acid reacting with an alcohol. And so the general reaction for this one will look like this, where here's our carboxylic acid, and here's our alcohol. The carboxylic acid, as part of its functional group, has got an OH group in it. The alcohol has got an H attached to this oxygen, and what you find in this reaction is that the OH from the carboxylic acid comes off, the H on the OH of the alcohol group comes off, those two get together to make water, and the remaining two molecules stick together to make something that looks like this over here, which now has a new functional group that we haven't seen yet, where we have R, C double bond O, O, R. That type of molecule is called an ester. Right? So this is different to any of the ones we saw yesterday, and you make esters from these reactions of carboxylic acids or things related to carboxylic acids with alcohols. And so this may well be a reaction that you've seen before, where you take some random thing and some other random thing, you mix them together with a drop of acid, and suddenly you've got something that smells like pineapples or bananas and stuff, right? Esters tend to be the molecules that are the fragrant ones. You can have other ones where you can mix a thing with a thing and a drop of acid and you make something that smells like vomit. I don't think you do those ones at school quite so much because boys would like that too much. But you can make fruity ones or very unfruity ones if you want. You can also do a reaction where you can take a carboxylic acid and react it with an amine in a general reaction like this. And so now what you do is the OH group of the carboxylic acid comes off, and the H, one of the H's on the nitrogen comes off. Again, those get together to make a water molecule, and we stick the two remaining pieces of molecule together, and now we make yet another new type of organic molecule with a new functional group again, where it's R, C double bond O, NH, R. And that type of functional group is called an amide. And so these are called amides. And of course these reactions are horribly important in biology because this amide group, as we call it in chemistry, is also called a peptide bond in biochemistry. And this is the sort of reaction that you have that joins amino acids together to make proteins. Right? So this reaction is happening probably 14 gajillion times a second in you as we speak. Right? As you're making proteins, and then when you want to get rid of proteins and enzymes and stuff, you have to break all these bonds, right? Which is actually really hard to do in the lab, but is very easy to do in your body, right? In the lab, you have to cook these up with like hot caustic soda. Obviously, you don't have that running around inside you. You have fancy enzymes that do that reaction for you. And we talk a little bit about one of those enzymes actually in Chem 191. We keep coming back to it in different parts of the course. Very, very interesting, cool stuff.